Hello viewers, welcome to the lecture Finite Element Methods and Analysis. Today we are diving into the review of elasticity theory, which is a foundational topic in unit number 1. This session will cover the key concepts you need to understand before we move into actual FEM analysis. Let us get started. What is elasticity? First, let us define elasticity. Elasticity examines how solid bodies deform under applied forces and return to their original configuration when loads are removed, but only if the material stays within its elastic limit. Think of this way. When you stretch a rubber band and let it go, it snaps back into its original shape. This is called elasticity. This reversible behavior is absolutely crucial because it forms the cornerstone structure mechanics and finite element modeling. Why does this matter for FEM? Because we need to understand this material behavior to set up our simulations correctly. Most engineering problems assume this elastic behavior within safe operational limits. So this shows about the mind map of the elasticity. So this linear elasticity you can see here assumes two things. One is small strain. So we are not dealing with massive deformations. The second one is direct proportionality between stress and strain. So if you double the force, you double the deformation within limits. So this linearity is absolutely essential for most FEM formulations. Why? Because it simplifies the governing equations dramatically, enabling efficient computational solutions to complex boundary value problems. Without this assumption, solving real-world engineering problems would be computationally prohibitive, and it is this linearity that makes FEM practical and fast. So let us see one by one. The first is about the stress. So what is stress? Stress quantifies in internal forces per unit area acting within a deformed body. Its essential intensity of load transmission through the material. Imagine a steel cube under tension, right? A stress is not just about the total force applied. It's about the how concentrated that force is across the cable's cross section. For a complete 3D description, we use the Cauchy stress tensor, a symmetric 3 into 3 matrix containing both normal stress components and shear stress components. At any point in a loaded body, three principal stress exist. They are the maximum stress, the minimum stress on specific planes, and where the shear stress vanishes. Understanding these is crucial for predicting the failure. So now we move on to strain. How materials actually deform. Strain measures the relative deformation of a material. It captures two types of deformation. They are normal strain and shear strain. So in this slide, we are seeing about the Hooke's law. So Hooke's law. What is Hooke's law? The Hooke's law focuses the constitutive relationship between stress and strain. In three dimensions, Hooke's law relates stress and strain tensors through a fourth order stiffness tensor that incorporates material properties. For isotropic materials, materials with same properties in all directions, we only need two independent elastic constants. They are nothing but the Young's modulus. It is denoted by capital E, and Poisson's ratio. So elastic constants. Elastic constants are nothing but they are the material properties. So let me elaborate on the material properties and their relationships. Young's modulus. It measures the stiffness in uniaxial loading. Stiffer material have higher Young's modulus values. Poisson's ratio. When you compress something, it bulges out sideways. This ratio quantifies the behavior. For incompressible materials like rubber, Poisson ratio approaches to be 0.5. Next is shear modulus. It is the resistance to shear deformation. It is mathematically related to Young's modulus and Poisson's ratio by the formula G is equal to E divided by 2 into 1 plus Poisson's ratio. Finally, bulk modulus. It is the resistance to volumetric compression. It is denoted by K is equal to Young's modulus divided by 3 into 1 minus 2 times the Poisson's ratio. So these relationships are fundamental. Once you know about Young's modulus and Poisson's ratio, you can calculate every other elasticity property. This is exactly what FEM software does behind the scenes when you input the material data. So next is about the boundary value problem formulation. When we combine three principles, that is equilibrium, kinematics and constitutive laws, that is Hooke's law, we get a system of partial differential equations for displacement. But here's the critical part: boundary conditions. We must specify either Newman boundary condition or Dirichlet boundary condition. These boundary conditions make the problem well posed unsolvable. Without them, infinite solutions exist. Analytical solutions exist only for simple geometries: a cantilever beam, a circular plate. Engineering problems require numerical methods, and that's where FEM comes in. FEM discretization strategy. So from theory to FEM discretization strategy, how does they become computation? There are four steps. The first one is the weak formulation. It converts strong form partial differential equations to integral form using variational principles. This relaxes the smoothness requirements. The second step is the domain discretization. You can see on the right hand side the image describes about the discretization. So it is nothing but subdividing the geometry into finite elements. It can be a triangle, it can be a tetrahedron, it can be a hexahedron, creating a mesh. So each element is connected by nodes. Nodes are nothing but the junction points. Step number 3 is the shape function. It is the approximate displacement field within each element using interpolation function. These can be quadratic or higher order polynomials or polynomials. Then the last step, that is nothing but the assembly. So constructing the global stiffness matrix, that is K, and force vector F, then solving the fundamental FEM equation. F is equal to K into U. So key takeaways, let us summarize the key takeaways. First, the elasticity theory provides the physical and mathematical foundation for all structural FEM simulations through three core principles. They are equilibrium, compatibility and constitutive behavior. Second, the understanding elasticity constant, Young's modulus, Poisson's ratio, etc. So it is essential for accurate modeling and interpreting the FEM result. Third, the boundary value problem directly translates FEM to FEM discretization. So elasticity theory is quite literally the gateway to computational mechanics. Finally, the linear assumptions, small strain and linear material behavior, simplifying governing equations and make computational solutions feasible for most engineering applications. Thank you for listening. We will meet in the next video. Thank you.